The model class encapsulates the geometry, textures, materials, and animations of a 3D model. The name string refers to the file name of the model. The vertex buffer array holds the model subsections that together comprise a full model. The data within a vertex buffer includes the positions, texture coordinates, tangents, and normals of a 3D mesh. The material array holds the diffuse, ambient, emissive, specular, and shininess lighting values that are used for Phong shading. The transform array holds the transformations, which are comprised of position, rotation, and scale values. Custom uniforms are variables for shaders that apply to the model as a whole. Buffered custom attributes are similar, but they reside in graphics RAM. Vertex trackers allow other entities to track the position of one or more of the vertices of a model. Bounding scale represents the size of the bounding box associated with this model. The entity and widget pointers refer to the game entity or GUI element that is using this model class. They are mutually exclusive, so they should be in a union. The points, normals, and texture coordinates represent the unsorted and unresized vertex elements that are read in from the model file. The sorted indices pointer is used to instantiate an array that will hold the correct order for the vertex elements to be accessed by the draw functions. The visible variable determines whether the model should be rendered and is set by the Scene Graph Manager. Disable Cull Face determines whether backface culling is enabled. Visible Stencil allows the model to be part of a stencil mask. The previous batch type enumeration keeps track of models that change rendering batch to facilitate certain effects. The Shadow Caster batch index specifies the shadow batch type this model will render in. The ID is the integer identifier for the model. The Anim Model ID keeps track of the model ID that is used for animation in the Model Manager. The Anim Vertex Buffer Index holds the vertex buffer index for the animation. The Attribute Array Index and Uniform Array Index are used to index the custom attributes and custom uniforms array, respectively. The number of UV channels variable is relevant in a rare case when a vertex buffer has multiple texture coordinates arrays. Array Index specifies which subscript this model resides in an array. Number of geometry indices indicates the number of unique geometry subsections of a model, in contrast to num vertex buffers, which counts vertex buffers that may have the same geometry but different textures. The Model Manager keeps a hash map of all the models and animations that only need a single instance. It first checks if the model's file name is already in the hash map. If so, it allocates memory for an individual transform and performs a shallow copy of the model. The shallow copy function does not copy any of the vertex buffer data, such as the positions, normals, and texture coordinates. After, we return the address of the model. If the model is not in the hash map, we create a new entry, then use the Read Model File function to parse in the data. The Read Model File function uses ifstream from the C++ standard library to read in the data from the model file. We check for the material and definition parse tokens, then we read the material properties and set the corresponding array elements. We invert the transparency value to obtain the opacity value. If the keyword we encounter is def for definition, followed by the geometry keyword, it indicates a vertex position list will follow. We increment the vertex buffer count, allocate memory for the array, then read in the coordinates. We set the number of vertices and set the geometry index. If the keyword is use instead of def, we refer to a vertex buffer by name and find the corresponding geometry index. This is necessary when a vertex buffer has the same geometry as another, but has a different texture or material. Next, we read in the vertex position indices. These represent triangles. We then read the normals and the normal indices. After that, we read the texture coordinates and the texture coordinates indices. We then read the transformation values, the rendering batch name, and the texture name. At the end of the function, we set the surface, material, and texture for vertex buffers that use another buffer's geometry. We then close the file. I use the VRML2 exporter for Maya. When it exports a model, the number of positions, texture coordinates, and normals often do not match. The match array to largest function resizes and sorts them so that they are in perfect correspondence. If the initial if condition is satisfied, then the normals have the largest array and we need the positions and texture coordinates array to match their size. We instantiate an array of normals and then set them to the values that we read in the file. We then create an equal amount of vertex positions and indices. The indices array will be used to reference all positions, normals, and texture coordinates upon a draw call. If there are animations for this model, we set the number of vertex buffers with animations, the number of animations per vertex buffer, and the number of frames of animation. We then allocate the animation frames by creating an array of vector pointers for each frame. Then we create an array of animation positions for each vector pointer. We check the sorted indices array to see if the position and texture coordinate array values have already been sorted into the correct position. If not, we set the correct position from the position array that was initially read in. We update the vertex tracker indices and the vertex animation positions to match the newly sorted index. We create the position index array and make it the same size as the normal index array. We then copy over the indices from the normal indices array. If there are texture coordinates, we follow the same procedure for them also. The next two conditions of the if-else if statement carry out the same sorting but are based on the texture coordinates array or the positions array being the largest array out of the three. We call free temporary memory to free all the allocations we needed before the vertex arrays were resized and sorted. If an animation is present, we set the animation model identifier and increment the count. The load shaders and textures function first calls the load texture function. This function checks whether there are any additional physics-based rendering textures that need to be loaded. In my engine, PBR textures are identified by having the type appended to the end of the primary texture name. I use the Windows function, stat, to determine whether these additional textures are present on the drive. If so, we set the texture names for the associated vertex buffer. We load in the primary texture and then the other PBR textures if they are present. The setup surface and batch function loads the shader and sets up any vertex attributes or uniforms that are needed to write into it. As we look at the deferred animation batch, we can see the shader being loaded and the ID being set. The load surface function checks if the shader has already been loaded by checking whether its name is present in the hash map, which associates its name with its ID. If it is, it returns the ID. If not, it allocates the surface, file names, and IDs. We extract the file type by looking at the last two characters of the file name. We then set the shader type to correspond. After, we create a new shader ID. If it is valid, we read in the shader file, then copy it to a character buffer for compilation. The validate shader function prints out errors and warnings from the result of the shader compilation. We then set the file name, ID, and shader type in the shaders array. The GL create program call creates a program ID, so we can attach the shaders to each other with the GL attach shader function. The GL link program function makes sure that the shaders are congruous with each other, initializes uniform values and addresses, and ensures shader resource limits are not breached. The validate program function calls glGetProgramInfoLog. This function retrieves the result of the linking operation. glValidateProgram in conjunction with glGetProgramIV allows us to know whether we have encountered an error whilst validating. At the end of the loadSurface function, we create a new entry in the hash map, increment the number of surfaces for the next load, and return the program ID. The addDeferredGeometryAttributes function calls functions addShaderModelAttribute and addShaderVertexAttribute. These allow us to cache the uniform and attribute addresses so that they don't have to be constantly retrieved upon every draw call. We then set the batch type. The setMaterials locations and setTexture location are artifacts of a period when I was using Phong shading for all models and need to be put elsewhere. Back in the loadModel function, we check if the model is supposed to go into one of the default batches. The default batches create batch rendering collections for anything that uses the typical rendering case. In my engine, it means that it is not for rendering shadows, tiles, or graphical user interface widgets, all of which have their own specific batch types. If the model is also shadow casting, it is added to one of the shadow casting batches. Rendering models within batches allows us to reduce OpenGL state change regarding aspects such as blend modes, shaders, and textures. There are 12 model batch classes currently extant in my engine, the simplest of which is the Model Batch Single class. This class allows models to be rendered one by one within one batch. It holds an array of model pointers and a count of the current total. The add function checks if the model has already been added. If not, it is added to the array, given an index based on its position in the array, and then the count is increased for the next model. The remove function checks if the batch index has been set. If so, it writes over it by moving all elements that are in front of it one position backward. The rendering function first binds the shader. It then iterates over the models in the batch, attaches the textures, sets the uniforms and attributes, then makes the draw call.